This video should be quite a bit more straightforward and shorter than the last one was. So this is about converting functions between rectangular and parametric forms. You can't always do this particularly easily, but there are some cases where you can. So the first example I want to consider is just the example we did in the previous one. So consider the parametrically defined function from the previous lesson. I want us to find the corresponding rectangular function by eliminating the parameter. So this was that one that we sort of did the table for in the previous problem. So could we find out what that thing was, right? Could we sort of do that? The answer is sure. What we could do is we can effectively take one of these expressions and solve it for t, and take that t and substitute it into the other equation, right? Doing that will allow us to get this in terms of x and y alone, which is a function notation that we're more comfortable with, I suppose. And we could do it either way. You know, I could solve this one for t, or I could solve this one for t. This one seems easier, so I'm going to do that. I'll basically end up with y minus 1 over 2 is equal to t. This is what I'm going to substitute into this other function expression. Doing this will get me x equals y minus 1 over 2 minus 2 squared minus 3. And I don't know that it's necessary, but it's worth thinking about how we could simplify this a little bit. So I'm seeing this as x equals 1/2 y minus 1/2 minus 2, so effectively minus 5/2 minus 3. I suppose if we wanted to, we could even sort of take that idea of the 1/2 that's clearly inside here, square that thing and factor it out. Like I kind of like the idea of pulling out 1/4 and making this y minus 5 squared minus 3. It might be worth pausing the video a second and checking whether or not you believe me that that's possible. But the reason I sort of like writing it this way is that when we write it this way, we can kind of see, hey, wait a minute, this is a parabola. This is a parabola that's x equals, so it's a sideways oriented parabola. It's a parabola that has a vertex of -3, 5. And so that means if I were to graph it, so like back 3, up 5, sort of got a point here, and then you've got the idea of a parabola like this. That's effectively what we said it was going to be. The difference is that ours didn't have an arrow down here, right? Ours started, quote unquote, started here because we had a time of -2 there, and the graph went around this way. So I don't want to say that the rectangular form and the parametric forms are the same. In fact, they're kind of different. The rectangular form gives you the entire curve with no sense of start or stop or orientation. The parametric curve really does start somewhere and moves through time to draw itself, right? But what this lesson is focused on is the idea that we can take things in parametric form and change them into rectangular form. I have one more example of that. It's a little bit more complicated, but we should be able to get through it. Alright, so here it is. Consider the parametrically defined function given below. I want to find the corresponding rectangular function by eliminating the parameter. In this problem, we could use the same strategy of solving one of them for t and plugging it into the other one, but it's going to be a lot uglier. Even if we just sort of attempted it right now, if you solve for this and got t equals the inverse cosine of y over 2 and plugged it in, like I could see us getting to 5 sine of inverse cosine of y over 2, and just saying like, okay, I don't want to deal with it. We could do some neat trig to work through that. In fact, I may do that at the end as a bonus for anybody that wants to stick around for it. But especially when sine and cosine are involved, I think there's a much more elegant solution. And that elegant solution is for us to stop and think for a minute and say, wait a minute, do I know any way to tie sine and cosine together? And this is a theme we have seen throughout the last few years we've been together. What is the most basic way of tying sine and cosine together? What identity do we have that lets us do things with sine and cosine together? What I hope everybody's thinking is we know that sine squared t plus cosine squared t equals 1. And the fact of the matter is that's an identity, which means it is always true. So what we can do is we can say, this little equation right here basically means that the cosine of t is y over 2. And this little equation means that the sine of t is x over 5. So what we can do is we can take this identity, which we know to always be true, and use those two equations, use these two statements to build this into an equation that won't have t in it, but will only have x and y in it. So try that. Should be very simple. So do that. Really, all you have to do is put the x over 5 in here and the y over 2 in here. You end up with x squared over 25 plus y squared over 4, and that's equal to 1. And what's really sweet is that we recognize that this thing is actually an ellipse. And hopefully we'll get a chance to sort of talk about that more. You guys will get a chance to see that. But like whoa, we get a chance to see that. I mean, we always knew that this 5 here, this 25 meant that the x radius of the ellipse was 5. The 4 here meant that the quote-unquote y radius of the ellipse was 2. There's the 2 sitting right next to y. There's the 5 sitting next to x. Like, this is just beautiful stuff. As far as I'm concerned, the video can end here because we did this thing. For those of you that want to sort of see the inverse trig magic behind this, if you've always sort of enjoyed that inverse trig, stick around for it. If you don't want to, I'll see you later. So if you're still here, you're kind of a hero. Like, I'm glad. So let's take a look at this. We could sort of think about the idea of what does this mean, right? What it means is there is an angle out there somewhere whose cosine is y over 2, whose adjacent over hypotenuse is 2, right? Now that I have that, we need to find the sine of that angle. Well, the sine of that angle should be opposite over hypotenuse. Well, that opposite side is the square root of 2 minus y squared, right? Just using the Pythagorean Theorem. So now we have the idea that x is equal to 5 times the sine of this thing. And the sine, of course, will be the opposite over the hypotenuse. So it'll be the square root of 2 minus y squared all over 2. And we're getting there, right? If I multiply that 2 over, I'll end up with 2x equals 5 times the square root of 2 minus y squared. If we square both sides, we'll end up with 4x squared equals 25 times 2 minus y squared. Oh man, and I just realized that that 2 all along was supposed to be a 4, I believe. Right, this one here should have been 2 squared, so that would have been a 4 there. This would have been a 4 here, a 4 here, and a 4 here. Right? So, carrying on, for those of you that are brave enough to still be here, 4x squared equals 100 minus 25y squared. 4x squared plus 25y squared equals 100. And finally, if we divide by 100, we end up with x squared over 25 plus y squared over 4 equals 1. You'll note that we got the exact same thing that we got up here. The difference is how much time it took us to get there and how elegant the solution was. The one that we did earlier using the sine squared plus cosine squared equals 1 trick, just a lot more simple, a lot more elegant of a solution, and that's what we're going for in math. So I'm glad to be with you this long. See you in the next one.